All right. Thank you very much, Michal. So I am going to show you today a novel interaction between open shell polar molecules. And this is all based on a paper that we hope to have on the archive this morning. It's not. So see this as kind of a sneak preview. I titled also the thing kind of like a movie. I see this as a sneak preview of this novel interaction. Now, I think a very quick summary of whatever we've already seen in the last few talks. We have collisions, ultracold molecules are lost. You know, we'd like to change this interaction at long range, for example, in microwaves and static electric fields. But I'm actually going to show you something slightly different. There's something that we can still check without external fields. Because what if we put things in different internal states? Now, this for Rydberg atoms, this has been kind of standard practice. You know, you put a Rydberg atom in some excited state, you get wildly different interactions. So why not study this for, molecules as well? Not Rydberg molecules, but hyperfine states in this talk. So the main thing that we're interested in is the dipole-dipole interaction between molecules. So let's get all ourselves on the same playing field in terms of the dipole. If we have a molecule in free space, we basically have zero dipole moment in a specific quantum state. Now, what does the dipole moment do very well? It does transitions very well. So you have the selection rule where you basically say, well, if you have to change your rotational quantum number by 1, and that kind of gives access to the dipole in molecules. Yeah, so I said molecules in one state don't have a dipole moment, so there's no first order dipole-dipole interaction. So what do we have? Well, we mostly have van der Waals interactions. If you have two molecules, let's see if I can make this work. Never mind. If we have two molecules in some state, you can have virtual excitation to some other state. This gives second order coupling, and it kind of basically splits these energy levels in a way that you get some attractive van der Waals interaction. And this is very well known for electronic states, where you have a transition dipole moment. But you can also have this for rotational states. And actually for the dipolar molecules that we all know and love in the ultracold community, this rotational contribution is actually way larger than the electronic one. So what happens if we put molecules in rotational states? Well, let's say you have two molecules in their ground state. You can have then a virtual excitation, by the selection rules, to the kind of first excited states of your rotational ladder. Now that energy level, that virtual level is above, so you get some coupling that is attractive, so an attractive van der Waals interaction. Now another thing that you can have is a resonant dipole-dipole effect, where you put your molecules one quantum apart, and actually that energy level, for example here the 1 plus 2, is at the same energy as the 2 plus 1. It is a resonant effect, and you get a first order R minus 3 interaction, usually resulting in very fast losses. Now what we found is if you actually put them 2 or more quanta apart, then you actually always find some kind of virtual state that lies below your initial state. And if the state lies below, then the van der Waals coupling will give a repulsive interaction in your initial state. So whenever you have two molecules, 2 or more quanta apart, repulsive interaction. We've shown in a paper from last year this can reduce losses by about 2 orders of magnitude. I won't go into more detail here, but the main thing that is important is that the strength of that van der Waals repulsion depends on the energy difference to your virtual state. And that difference needs to be as small as possible to get a strong interaction. So what we want is smaller energy difference. So how can we achieve that? By going, to hyperfine states. And spin states have way smaller coupling, and you could perhaps achieve very strong van der Waals interactions there. So okay, what is hyperfine structure? We have electron spin, we have nuclear spin, and we have rotation of the molecule. This all together couples to some total angular momentum F, and this F labels our hyperfine states. Now this also has a selection rule, so we can change that F by 0, plus or minus 1, but not more. And also 0 to 0 is also not allowed. So let's put an example. This calcium fluoride, kind of one of the our quintessential laser coolable molecules. It has a single electron spin and a single nuclear spin. And the energy levels look like this. By spin-spin coupling in the ground rotational state, you get 2 energy levels. And at the higher rotational state, you get additional spin rotation coupling, you get 4 energy levels. And all on the order of tens or hundreds of megahertz. So okay, we now have access to basically putting 2 molecules in some rotational state and some hyperfine states within there. Now, what are the interactions that we can get? The kind of interesting thing here is that the state is always degenerate with kind of its resonant state in a way. Now, it depends, whether it's truly resonant, it depends on whether the coupling J, this is a laser pointer, it's really annoying. The coupling JF to J prime F prime, whether that's allowed. And so based on the selection rules, that can be allowed. If it's allowed, we get resonant interactions. If not, then we get van der Waals interactions. And then actually we want van der Waals interactions to virtual states that are within our rotational manifold. Those are very small energy difference. And the only way to do that is to put one molecule in J equals 0 and one molecule in J equals 1. If we do that, then depending on the selection rules on F, different interactions can happen. So for example, if you put a molecule in F equals 0 and F equals 1, that has a kind of a transition that is allowed. And so that would give, if you put molecules in these two states, that would give resonant dipole-dipole interactions. So these R-3 ones that lead to fast losses. But if you, for example, put them both in F equals 0, then there's no coupling between them and giving van der Waals interactions. So let's put all of these states together in one picture. These are all kind of the pair states of the molecules. All the states shown in black have this resonant dipole-dipole interaction, and the ones colored have van der Waals interactions. And whether they're repulsive or attractive depends on kind of the relative positions of all these energy levels. And we actually find for calcium fluoride that there is indeed a level, this 0+2, that couples to something slightly below, and that will basically make a very repulsive interaction within that state. So let's do that more quantitatively. We can look at interaction potentials. So again, these are our initial states that we can choose. We then throw in a dipole-dipole operator, and we get something that doesn't really work well on this screen. Doesn't matter that much, the colored ones are most important. We see that kind of these two states that are colored, they have van der Waals interaction. There's either an attractive or a repulsive one. Now this repulsive one for the 0+2, at some point it couples with all kinds of other channels, it bumps up and down, whatever happens. But the idea is at ultra-cold temperatures, we can use this kind of barrier to effectively shield or lower collisional loss between these two molecules. So what we can do full coupled channel scattering on these potentials that I just showed you, and then you get loss rates. So I show here loss rates as a function of the temperature. If you put them in any of these curves that were in black in the last slide, then you get resonant dipole-dipole interactions, and that leads to fast losses on the order of 10⁻⁹ cubic centimeters a second. And now what I say is, okay, we want it to be in the state that I showed in blue. So you can effectively say, okay, we're going to flip the nuclear spin. Oh, there you go. Minor change, a nuclear spin flip. How much can the dynamics change? Well, we're basically turning off then the dipole-dipole interaction. And so you then get loss rates that can be lowered to about 5 orders of magnitude below this resonant dipole-dipole. Just by flipping, for example, a nuclear spin or changing your spin state. We've seen this word already a few times now, but there's a kind of universality in all of this, where if you put things in dipole-dipole units, the main thing that it depends on still is how big your hyperfine structure is. So you can kind of blow this up by scaling the whole hyperfine structure, and that's kind of what I plot here on the x-axis. And you see the bigger your hyperfine structure becomes, the bigger this barrier of this repulsive potential becomes, and you basically lower your loss rates dramatically. And this holds very well for open shell molecules, because you have electron spin, has large hyperfine coupling. If you look at the bialkali, they would lie somewhere on the left of the plot, right? You have couplings that are about 3 orders of magnitude below, for example, calcium fluoride. So unfortunately for the bialkali, this hyperfine van der Waals interactions might not really result in suppression of loss. Now, calcium fluoride, of course, is not the only open shell molecule. We have a few others. Let me actually skip that. We have a few others. So, other earth alkaline monofluoride series, but also yttrium oxide. These are all kind of these open shell molecules with large hyperfine coupling. And especially yttrium oxide is interesting because that is such a stable interaction that it, compared to universal loss, the interaction between two of these molecules in these specific hyperfine states can actually be reduced by about 8 full orders of magnitude, which is insane given that we're changing spin state. Can this be measured? Well, we hope so. I think it's possible to kind of isolate these interactions in a way. Because you have to have two molecules that are in different spin states, and they need to interact. So our solution will be to merge tweezers. So you put two molecules in tweezers, you change their internal state, you then make them collide and measure whether they're lost or not. And you would, hopefully be able to see, 5 or even 8 orders of magnitude suppression of your collisional loss. And so, as a theorist, this sounds really cool to me, because it just sounds like a lightsaber battle. Also Luke Skywalker, he suffered from collisional loss. He lost his hand after 1 minute. But if he listened to this talk, I think he could have extended that to a few months. So I think that makes us the better Jedi here. Anyways, in conclusion, I have shown a novel interaction, which we term kind of hyperfine van der Waals interaction, between open shell polar molecules. I shown that we can kind of switch on or off these dipolar interactions by changing the spin states of your molecules. And I've shown you that we can decrease loss rates for a few open shell molecules by up to 5 or even 8 orders of magnitude. With that, I come to the end of my talk. I just want to advertise myself shamelessly by saying that my PhD is also coming to an end, and I'm also looking for postdoc opportunities. I'm all week here to have a chat if someone is interested to have a chat. Okay, thanks very much.
I would suggest that you can stay in Warsaw much longer than 1 week. But we can talk later. Okay, time for questions.
Okay, good enough. All right. So, well, you made it like a big deal for, well, you change one hyperfine flip spin, and then you have a change in 5 or 3 orders of magnitude of collision rate. But that's, of course, well known. When you collide atoms and spin polarized molecules, when you both spin polarize them, even atoms, right? You can have spin exchange rates that are much higher than would be like spin relaxation rates. Just a comment, may not be that new.
I see. Thanks for your comment.
I would like to add that Luke Skywalker lost his hand in a light-assisted collision.
Okay, Jacek, over there.
Hi, can you please reiterate why exactly you needed the two molecules to be in different rotational states even when you put in the hyperfine structure in there? Like you had one in J equal to 0 and the other in J equal to 1?
Yeah. Let me just go back to that slide. Yeah. Basically, you can ask yourself what... oh, that's not what I wanted. I put there very generally some JF and J prime F prime states. And these hyperfine van der Waals interactions, you basically want a very small energy difference to a virtual state. So you want coupling basically of, for example, the 0+2 state to something within the rotational states themselves. Now, if you put molecules in rotational states that are not 0 and 1 or even 1 and 2 and such, you will actually get these rotational van der Waals interactions that I showed you before. You get mainly coupling to the states that are further apart on the rotational energy ladder. So in order to get coupling from this, for example, the 0+2, it actually couples to, if you should look below, the 1+1 minus. In order for coupling for that to occur, also the selection rules on the rotational states need to be taken into account. So that's why we need to be kind of in two states that are 1 quantum apart.
Okay, I see. So it doesn't really get better if you had access to, suppose, an F equal to 5/2 or something larger than that in one rotational state. It doesn't necessarily get better with that. So right now you had access to, suppose, F equal to 2, which is the highest angular momentum. If you had access to a much higher angular momentum, let's say with a larger nuclear spin or something like that, it doesn't improve things here.
It depends very much on the molecular structure itself as well, because it depends actually on really what the relative energy levels are. Whether you are an F equals 2 or an F equals 5/2, or for my part F equals 100. As long as there's some coupling to something nearby, you could have these interactions.
Yes.
Thanks. Thanks for a nice talk. I have a slight question. The mixture is a non-coherent mixture between two states, right?
Yes.
So how can you avoid collision between 0, 0?
Yeah, so very, very good observation. If you take a full gas of molecules and you take, one half in one state and one half in the other state, you will still have fast losses between like molecules. So applications of this would likely lie more so in systems with tweezers or quantum simulation where you have more isolated collisions. Full gases of this stuff, this is not really where you can see the suppression of loss, because like you say, you still have collisions between like partners. Yeah.
Yes. So maybe I will comment in the meantime that somehow the shielding here is also a bit similar to mechanisms that Bridget shown for this excited state, that for the zero field shielding, we get like 2 orders of magnitude suppression because of the a mismatch in the rotational constant. So there is this, but okay, we can.
Yeah, hi. So my question will reveal that I didn't understand the confusion is, oh, it sounds great that I can make an energy splitting between 2 levels smaller and smaller by using hyperfine energies, but if there's no coupling, it doesn't buy me anything. So if I want to bring in hyperfine to help me out to make some coupling strong, it sounds like I need necessarily some spin rotational coupling or something like that. And if that is weak, it will suppress the rate. Am I right or no?
I think so, if I understand you correctly. I think you're right.
One needs spin rotation coupling. Something that mixes S and J. Which is fine. We can have that. It's just like an additional piece that is required.
I think so. But I'd have to think about it a little bit more. Not in front of a camera. No, but I'll think about it. Yeah. But I think you're right.
Yes.
One thing I talked with Bridget in demo is that maybe people can think of a way to to suppress both the loss between for mixture, okay, between the same spin state and the different spin state. This is probably important for fermion molecules, because if you can do that, then you can study 2 complement fermion molecules. You can, instead of focusing on only P wave fermion molecules, then you can have S wave also.
Yeah, we work with Bridget. We work with Bridget on exactly something like this that you are mentioning. Okay, the last very brief question. Okay, John, please.
So a comment and a question. So in terms of experimental access, in fact, with CAF, they have been put in tweezers and collisions actually have been observed, but not in the particular state combinations that you pointed out. Now, my question concerns a plot you showed on MGF and CAF and YO. So they all have very different amounts of suppression and loss. Is this really all determined just by the hyperfine coupling? Or
yes, exactly.
Is there more?
Yeah, no, it's really determined by where exactly these energy levels lie with respect to each other. So I have, if you then look at, for example, interaction potentials, they're actually quite different. I mean, let me see here. They all have this, similar spin states, but the relative energy levels determine, what coupling takes place, and it's actually, quite complicated once you get into shorter range. But all of these are in a way quite different, depending really on this coupling of hyperfine. Yeah.